Maybe it's better if you talk.
No, you say hello. You say hi, everyone. You say hi, everyone.
Hi, everyone.
No, but if you don't jolly this.
Hello. Yeah, no.
Okay, I'll
Go on, you do it.
just interject between
Okay.
Okay. Hi everyone, thank you for following along with the Christmas Advent Calendar puzzles. We really appreciate you solving the puzzles and leaving your comments below the videos. Do you have anything to say, Matt?
No, except for thank you for doing the puzzles.
God, you're terrible at things. This was a really hard puzzle.
So where are the 7 lines again?
So there are now 1, 2, 3, 4, 5, 6, 7 rows of 4 Rochers.
Right, so it says, Santa said that we've got all these mince pies on his own. He can eat them it takes him 20 days to eat them. But if Mrs. Christmas helps him, then they can eat them all. This is okay, this is okay. Right, if Mrs. Christmas helps him, they can eat them all in 12 days. Okay, so Santa on his own takes him 20 days. Santa plus Mrs. Christmas. 12 days. Now, I think the easiest way to do this is, what's the question asking again? How long would it take Mrs. Christmas to eat it by herself? Right. So, the easiest way to see this is to say that if Santa is getting help to eat them, they eat them in 12 days. If Santa was eating them on his own, after that 12 days, he'd need another 8 days. So what that means is, in the amount of time it takes, the amount of mince pies that Mrs. Christmas eats in 12 days, so 12 days worth of Mrs. Christmas mince pies, Santa would need another 8 days to eat. So what Santa takes 8 days to eat, Mrs. Christmas takes 12 days to eat. So in other words, Mrs. Christmas takes the amount of time that Santa takes plus half the amount of time again. So if Santa was going to take 20 days to eat them by himself, Mrs. Christmas would need 20 days plus half that amount of time again. So she would need 30 days. Right, Secret Santa puzzle. This is a great example of us thinking of a problem and then not realising that it was slightly trickier than we thought it was going to be when we first thought of it. So the question was, you got 7 people, you got 7 names in a hat. They each choose a name from the hat. What's the probability that when they do that, none of them have chosen their own name? So they've all randomly chosen someone else's name from the hat for the Secret Santa, right? Right, one way of looking at this is this way. So you've got 7 people, let's number them from 1 to 7. And so person 1 picks a number, and it can be any number as long as it's not 1, right? And then person 2 picks a number, I know their names, pretend they're numbers, They've got to pick any number out of the hat, as long as it's not number 2. And this one picks as long as it's not number 3. So what we're really asking here is, how many ways are there of rearranging the numbers from 1 to 7, but rearranging them in such a way that none of the numbers are in the place where they originally were. Okay? And in math, this is called a subfactorial. And the formula for n subfactorial is, it's written like this. Grace is holding the formula up for me just so I don't get it wrong, because we are
we're professionals.
Because and we don't have any time and we can't afford to mess this up. So it's the sum of k is 0 to n of the sum of -1 to the power k over k factorial. I would like to explain to you why this formula is what it is, but the amount of time that we currently have does not permit me to actually do that. So it's a bit like Fermat's proof, isn't it? When his margin wasn't big enough. Yeah, Fermat's margin wasn't big enough, and our time slot before people start arriving in this room isn't big enough. Anyway, so what we want is, if I do 7 subfactorial, what did it say it was, the computer? 1,000.
1,854.
Right, so apparently there are 1,854 different ways that you can rearrange these numbers so that none of them are in their original place. But we know that 7 factorial, which is just the number of ways of rearranging these. Where's the factorial button gone? Oh, there it is. Is 5,040. So the probability, if everybody takes one out, that nobody's going to get their name is just that divided by that, isn't it? If I can do that, which is 1,854 divided by 5,040, which is 0.3679 to 4 decimal places, which is
About 37%.
About 37%, which is an interesting number, isn't it? 37. 37 was the answer to another puzzle, wasn't it? But maybe we'll do a video about number 37. But that's the answer. So actually quite likely, really. Quite likely. Which makes me wonder whether we've got it wrong. Can you, if you... So you investigate this yourself, and if we've made a mistake, tell us, and that would be very interesting. Right, the Christmas tree puzzle, this is how this works, hopefully. So, the farmer looks at all the columns and looks at the shortest tree in every column, and then labels the tallest of the shortest trees, A. So A is tallest of shortest. Then he looks at all the rows and found the shortest tree in every row, and then labelled B as the shortest of the tallest in each row. Okay. And the question was just, which tree is bigger? Tree A or tree B, and it's quite confusing because it's just tallest to the shortest and shortest to the tallest and all this. And the trick is to find a tree that is in the same row as B, in the same column as A, or we could have done the same column. Why not just choose this one here? So if we think about this tree, it's in the same column as tree A, but also is in the same row as tree B. Well, it doesn't matter that B is the shortest of the tallest trees. B is the tallest tree in the row that it's in. So B is taller than this tree here. And it doesn't matter that this is the tallest of the shortest of the trees in each column. This is still the shortest tree in its column. So this tree is shorter than this one, but this one is shorter than this one. So A is shorter than B.